All right, before we explore complex eigenvalues, let's just review a little bit about complex numbers. Probably something you haven't studied in a little while. Remember that the definition of I, it's the square root of -1. So square root of -1 is I. That's an imaginary number, right? We'll talk about complex numbers, how that fits in as well. So first thing I guess you probably remember this is that there's this whole idea of powers of I. If I is the square root of -1, then I squared would be -1 if you square the square root. I cubed can be thought of as I squared times I. If I squared is -1, that's going to be -I. I to the fourth is I squared times I squared, which means it's -1 times -1, which is 1. I to the fifth can be thought of as I to the fourth times I, which means it's just going to be 1 times I, so it's I. And what happens, every fourth power of I, this pattern just recycles itself. We have I, -1, -I, 1. I, -1, -I, 1. And I guess that's just meant to show you that you can take any power of I and simplify it to one of those four values, either I, -1, -I, or 1. Okay, so that's one thing. This idea of a complex number, for example, sometimes you might solve a quadratic formula and you get 3 plus or minus 2i. So the whole thing isn't imaginary, right? Only the 2i is. So we call this generally a complex number. So a complex number, if you have something like a plus or minus b times I, a is the real part, and b is the imaginary part, the bi term. Okay, and that will become important. Finally, this is something you may or may not have seen. Sometimes in a pre-calc class when you're reviewing trig, they talk about this formula, Euler's formula, and it's kind of an intriguing formula. What it says is if you raise e, the number e, to the I, square root of -1 times theta, maybe it's some angle, that it equals the cosine of theta plus I times the sine of theta. In other words, this can be written as a complex number, right? This is a real number, that's an imaginary part. There's a whole story behind that. If you're curious, you could look it up. It's not that important that you understand how this formula is derived. One cool result of this, though, that is just so cool, you can't talk about Euler's formula without mentioning it. If you plug in pi for theta, what do you get? You get e to the I pi equals cosine of pi plus I sine of pi. Cosine of pi is, of course, -1. Sine of pi is 0, so this part goes away. This is nothing, plus 0. And if you, the way we usually talk about this being very cool is if you move this over, what do you get? You get e to the I times pi plus 1 equals 0. And this is just sort of an interesting equation, kind of a famous equation. Because why is this? Well, if you think about in your math career, what are 5 of the most interesting numbers that, well, at least that you've gotten the perception that math teachers think are interesting? I mean, certainly pi's on the list, right? Pi. E has been a very intriguing and useful number in calculus, as we've seen. I, the square root of -1, is kind of an interesting number. 1, you have to agree, right? 1 is a very interesting number. 1 times anything is itself, right? And 0, right? 0 is a very interesting number as well. So this is an equation that links 5 of the most interesting numbers to mathematicians. So there you go. Just had to throw that in there. Okay. So now we can start to talk about what happens with a linear system of differential equations when you get complex eigenvalues. So here's our linear system. We've got some initial conditions for x and y. The matrix associated with that, just the coefficients, -1, 2, -3, -1. If we find our eigenvalues using our determinant, with the negative 1 minus lambda, negative 1 minus lambda on your main diagonal. Keep the off diagonal the same. And then remember the determinant is this times this, the main diagonal product minus the off diagonal product. So you're going to get negative 1 minus lambda squared minus negative 6 really turns into plus 6. Now we could FOIL this out and refactor it, or maybe since it's a perfect square here, what if we just move the 6 over, take the square root, it's going to have to be plus or minus the square root, and then if we solve this for lambda, we're going to get negative 1 plus or minus I root 6. So we have complex eigenvalues. And okay, one thing you'll notice too is the eigenvalues will always come in pairs like this. We call these complex conjugates. If one of your eigenvalues is negative 1 plus I root 6, the other one's going to be negative 1 minus I root 6. So those are referred to as complex conjugates. Now the real part, which we'll call A, is negative 1, and the imaginary part with the I is root 6, so B is root 6. Okay, as far as actually writing the solution, when you have complex eigenvalues, it is, for lack of a better word, it's complex. It's a lot of work. So the book has some problems where they do write the general solution, and so we will discuss that in a future video, because that's a long story there, how to actually write the solution. Many times, however, we're just interested in what's the behavior of the solution, right? What does it do? Is it stable? Is it unstable? What do the solution curves look like? So let's just consider right now what part of the solution would look like. And so let's just take one of the eigenvalues and one of the eigenvectors, and we'll plug it into our general solution formula. Remember, it's C1 e to the lambda t times, I'm not even going to find the eigenvector. There would be some vector there. Okay, what you could do, the t could get distributed, and using, you'll probably be familiar with this from 17b, we can unsimplify this to make it a product, e to the negative t times e to the I root 6t. And the purpose of that is now we can think of this term as e to the I. If I think of that as like theta, I can use Euler's formula for this part of the solution. So it would become C1 e to the negative t, and then if I plug that in for theta, cosine theta plus I sine of theta t times some eigenvector, okay? Now there's a lot more to the solution. Like I said, there's another eigenvalue and another eigenvector, and dealing with the eigenvector is part of the problem there. But we can tell a lot just by taking it this far, because you can tell with this solution, any equation you've ever graphed in your life that has cosine and sine in it, you know what it does. It causes curves, right? It causes oscillations in the graph. So this part's going to cause oscillations in our solution. And what's going to happen to those oscillations comes from this part right here. As t goes to infinity, we know that e to the negative infinity would approach 0. That's going to make, so eventually, I can tell just from here that my solution's eventually going to go back to 0 for both x and y. So I already know this is going to be stable just from this right here. But then taking these things together, if my solutions oscillate and they go to 0, if I look at individual solution curves for x and y, like here would be x of t, here is y of t. Remember, my initial condition was 2 for x way back at the beginning. What this tells me is x would follow something like a sine or a cosine graph. But what would happen is the solution would start, the oscillations would decrease, or the word we use for that is dampen. Okay, these oscillations will get smaller and smaller, so eventually it'll approach 0. Same thing for y. Our initial value for y was 0, and we will see oscillations that also dampen over time. Now, we've also been spending a lot of time visualizing solutions on the phase plane. Remember, the phase plane, what you're doing is you're basically sketching, you're modeling these individual solutions together as a point. So like, for example, if my point was negative 2 sorry, if my point was 2, 0, what I would see, okay, we'll talk about the direction here in a second, but if the graph looks like this, what happened to x at the beginning? X started to decrease, right? And if you follow this spiral, you'll see your x value starting to get smaller, right? And now it's negative, and now my x value is positive, but not, it never quite gets as far as it did before, and then it's back to negative. So that's exactly what's going on here. X is positive, negative, now it's positive, but not quite as positive, right? So yeah, so x, this solution's in there, and so is y. Think about my y coordinate as we move from here around this spiral. What's happening to my y? It's decreasing. What's happening to my y? It's decreasing, right? And then what happens is my y value starts to increase again, and now we have positive y values, right? It's going to move up here and get positive, and then it goes back to being negative, but not quite as negative. And so that's how this solution is also built into that. Okay, I'm going to focus in on this. Okay, as far as, so we call this, first of all, this would be called a stable spiral. Stable because eventually my solution will get back to 0, 0, and it looks like a spiral. Now, sometimes they'll want to know, they'll ask you, okay, we know it's a stable spiral, but which way does it spiral into the origin? Because what the full story is that I'm having mine spiral. This is a motion that's called clockwise, right? Just like the clock, the hour and minute hand work on a clock. This is spiraling clockwise inward. But in another problem, I could have one that's spiraling counterclockwise inward. So to see what the solution trajectory looks like, whether it's clockwise or counterclockwise, what you can do is test your initial value. It'd probably be the best place to test it, which was 2, 0. What I mean by test it is if you plug that back into your original differential equations, negative 2, I think it was negative x plus 2y. So we get negative 2 plus 2 times 0 gives me negative 2 for dx dt. For dy dt, we get negative 6. So what that tells me is my initial motion from this point moves to the left, right, by negative 2. That's the x motion, and the y motion is downward. And you can think of this together as a vector, negative 2, 6, a vector that goes left 2, down 6. So that vector, if you drew it from here, and you knew it was a spiral, and you knew the vector was going this way, well then it's got to be spiraling clockwise, right? If it was going counterclockwise, I would have expected a vector going up like this, spiraling this way, right? So that's how you tell the motion, the solution trajectory. Okay, so to summarize this, anytime you get complex eigenvalues, your eigenvalues are going to be a plus or minus b times I. A is the real part. To determine the stability, it's all going to be about A, the real part of your eigenvalue. Again, here's down below here, here's sort of your general solution for part of it, right? I don't have the second part, so maybe I should put plus dot, dot, dot. We're going to end up using Euler's formula for the imaginary part, so that's going to cause the oscillation, and oscillations now we've seen on a phase plane will look like spirals. But as far as the stability goes, it's all about what happens to these oscillations as t gets bigger. If a is bigger than 0, if a is a positive number, like 2, then e to the 2t, that would go to infinity when t goes to infinity. So what that tells me is my oscillations will get bigger over time. The spirals will grow. They'll oscillate and grow. So individual solutions, you would expect a kind of a sine or cosine wave where the amplitude's getting bigger. Same thing for y. I'm putting both of those on the same axes. And as a phase plane, that would mean whatever your initial condition is would spiral, but the spiral would go outward away from the origin. And again, just a note, I'm just making up a random one. I have mine going this time counterclockwise, but they can go clockwise or counterclockwise. If a is less than 0, that was the example we just looked at, you will get oscillations that dampen, and that would be called a stable spiral. Okay, these are all spirals, stable spiral. The one up here was an unstable spiral. And then the third situation, if A is equal to 0, meaning another way to put that is you have purely imaginary eigenvalues. So say you get plus or minus 2i where there's no real part to that. Well, if you go back to the solution for that, let me move this up for a second. If A is 0, this is going to be e to the 0, which is just 1. And what would happen then is I would get my oscillations, but the amplitude would always stay at 1. They're never going to get bigger. Well, maybe bigger than that depending on the constant, but it's never going to change, okay? So what that tells me is, well, let's do individual solutions. If I was looking at x would oscillate, but the oscillations would stay at the same amplitude. Y doesn't have to have the same amplitude, but what will happen as x, but it will remain constant as well. As a phase plane, what we see how that gets looked at is it looks like doesn't have to look like a perfect circle. Oftentimes you'll see it look like an ellipse, but essentially it's a spiral that just repeats itself, okay? It doesn't go inward or outward. And so that's called a neutral spiral, sometimes called a center. So a couple practice problems. Say I want to classify the stability and what direction the solution trajectory will go, meaning will it be clockwise or counterclockwise? So both my examples are going to be spirals. So this matrix here, it's all about the eigenvalues. If you do the math, you'll end up getting 3 plus or minus I root 39 over 2. And if you split that up, 3 halves plus or minus I root 39 over 2. The minute I see that, well, the minute I see a complex eigenvalue, I know it's a spiral. And the minute I see that the real part is positive, that would be my A, then I quickly know that's going to be an unstable spiral. So I've already got, let me show that. Once I know this part is real and positive, then I know that's an unstable spiral. To determine the motion, whether it's going to be an unstable spiral that spirals counterclockwise or clockwise, remember that that matrix really stands for this system of differential equations. And you might pick some test points here, right? We didn't have any initial conditions, so let's just pick, and you can pick more than one. Say I pick 1, 0. If I plug x equals 1, 0 equals y into my two differential equations, I get a value of 2 for both dx dt and dy dt. And that would be translated as a vector that goes over 2, up 2, which would be a vector at like a 45-degree angle. At 1, 0, 1, which is an easy point to evaluate, if I plug 0 for x and 1 for y, I'm going to get negative 5, 1, which is a vector that goes to the left 5 and up 1. So it's going to be moving up and to the left. Now you can use those vectors to kind of visualize what the solution would look like. Okay, at 1, 0, I have a vector going this way. Now if I know it's a spiral, right, that's part of it. If I know it's a spiral, then I know it must be moving this way, not the other way. So I can anticipate that this spiral is going to go counterclockwise. There was my vector here, right at 0, 1. So that vector is going off like this, and it's going to spiral outward counterclockwise would be my direction. One final example here. Maybe here what I would say, take a second, pause the video, see if you can work out the eigenvalues and what the stability would be classified as and whether the solutions go clockwise or counterclockwise. Okay, assuming you did that, here's what we get. This time, my eigenvalues come out to be purely imaginary. no real part to my complex number, so I know it's going to be a neutral spiral. And then to determine the trajectory, there's my two differential equations, and I'll pick a couple test points like 1, 0, and 0, 1. 1, 0, I get a vector going upward, 2, 5. At 0, 1, I get a vector going downward and to the left. And so interpreting that on my picture, I know it's a neutral spiral. I'd have my motion's going to be from here this direction, so kind of like the last one. And then if this one's downward, right, like this, that would fit a solution trajectory that is going counterclockwise. That would match up with that. So this is a neutral spiral that moves counterclockwise. Okay, on the next video, we will talk about how to write the solution to a linear system with complex eigenvalues.